Swayam Prabha. Digital India. Educated India.
Theoretical properties are concerned, when it comes to practically solving linear equations. So I'm going to again say that this is a square system of equations. A is n cross n, x is n cross 1, b is n cross 1. As far as practical, theoretically we know when there is a solution, when there exists, when there may not exist a solution. But as far as practice is concerned, if I give you an arbitrary matrix, there are certain matrices which are diagonal matrices, which means only the everything else apart from the diagonal is 0. So only on the diagonal entries are non-zero. Right? Now there is other set of matrices, upper triangular or lower triangular. What that means is everything below the diagonal this is an upper triangular matrix and this is a lower triangular matrix. Now if I gave you then I give you a general matrix. There is no specific structure. There could be things which are 0, non-zero. There are things which are non-zero everywhere. Now I give you these 4 kinds of matrices and I ask you, I give you some right hand side. Right hand side is the same or may not be the same. Now which of these systems of equations is easiest to solve? The diagonal matrix. See, the diagonal matrix is easiest to solve. In fact, from each row equation you can find the solution to one. And therefore the diagonal matrix is the easiest to solve. Upper or lower triangular, both of them it is not as easy as to solve as diagonal matrices, but it is not as bad also. And we will see why that is the case. Because if you take an upper triangular matrix, you look at the last equation, that has only one unknown. So you can solve for the last variable from the last equation. From the last equation you can put it in the previous equation. There are only 2 unknowns and out of them one was known. So you can solve for the other. And so on you can go, this is called backward substitution or backward sweep. So in upper triangular matrix you can solve for all the variables without too much effort. A diagonal matrix is easiest to solve. By looking at the matrix you can find the solution because you just have to take ratios of the right hand side to the diagonal entries. Upper triangular seems to be slightly difficult, but it is not so difficult again. You can just have to solve it step by step. Start from the bottommost row, solve for the last element and you keep going backwards. Lower triangular is equally easy to solve. Why? You just start not from the last row, but you start from the first row. The first row has only one variable, so you solve for the first variable. The second row has 2 variables, so you solve for the second variable and so on, and you do what's called a forward sweep and you can solve for this. Now for arbitrary matrices, what do we do? Right, this is an arbitrary matrix and it seems to be very difficult. It's neither diagonal nor upper triangular or lower triangle. What Gauss elimination tells us is there is a systematic way of converting into an upper triangular matrix and then we solve that. So how do we do that? That is again, I will not give you the complete algorithm. I'll just work with you for this particular example over here and you should be able to generalize this for other systems. So what we do is we try to make a 0, we try to make it an upper triangular matrix, which means all of these have to become zeros, all of these have to become zeros eventually. So we try to make it an upper triangular matrix because we know how to solve upper triangular matrices. So what we do is, I'm going to take the second row and use the first row to make a 0 in this element of the, in the 1, 2, 1 element over here. How do I do that? I can do R2 plus 3R1, but I'm not going to write it as plus 3R1. There is a reason I will come to that later. I'm going to write it as minus of minus 3R1. So if I take 3 times the first row and add it to the second row, what happens? So I have taken R2, take 3 times the first row and added to the second row. Nothing happens to the first row, nothing happens to the third row. The second row, what has happened? Minus 9 plus 3, it becomes 0 over here. Then I get 0, 5, 5. Nothing is. Now I do likewise. I need to make a 0 over here. So what I do is R3 plus 3 times plus R1, because I just take the first one, add it to the third row, I will get a 0 over here. But again, I am going to write it as R3 minus of minus R1. Right. So we are partially successful in converting into a upper triangular matrix. We just need to convert one more element over here. We need to make a 0 over here. How do we make a 0 over there? We take R, and at the same time we should not destroy the other zeros that we have got. So the only way to make a 0 with this is not to use R1. If you use R1 to make a 0 over here, then 3 over here will come and mess it up and give you a 0 in the third row. So the only other row which is available to you is the second row. So we try to get a 0 in the 3, 2 position over here by using the second row, and we do that by R3 minus 5 times R2. So I get 3 minus 5 minus 3, 0, nothing happens to the second row, 0, 0 and minus 4. Yeah. This is minus 2, minus 11 and 50. Lo and behold, we have got our upper triangular matrix over here. So let me call this U, and this is easy to solve, as I said, right? Because you know minus 4 x3 is equal to 50. So x3 is equal to, in this case it is minus 12.5. So we have 5x2 plus 5x3 equal to minus 11. So I know x2 is equal to 10.3 in this case, and x1 is equal to 4. So this is Gauss elimination, and they can algorithmically code this for an arbitrary large set of arbitrary large system of linear equations. And you'll be doing some examples on this, and you'll see certain times the procedure may break down, and you'll figure out what to do when that happens. Right. So the basic idea is to convert it systematically into an upper triangular matrix, and then do what is called backward sweep or backward substitution and solve for the variable starting from the last variable onwards. Okay, so now what I really did in the previous case was I had this matrix. I had this matrix A, and then after substitutions I got the matrix U as 3 minus 5 minus 3, 0, 5, 5, 0, 0, minus 4. Now it turns out that I can write the matrix A and the matrix U are related to each other, and they are related because they were doing only some row operations on the previous matrix, and you can show that A can be written as L. L is a lower triangular matrix with a very specific something more. L has ones on the diagonal, and U is this particular matrix over here. This is my matrix U over here, U. Now this is a lower triangular matrix, everything else is 0 over here. Now it turns out that the other non-zero entries in the lower triangular matrix, could you guess what they were? That's why I wrote it in a pretty particular manner in the previous case. Okay, let me give you a hint. This was minus 3, this is minus 1, and this is 5. So the entries in the lower triangular part of the matrix are basically the multipliers, negatives of the multipliers. That's why I wrote it in a very specific manner, right? I wrote it as R2 minus of minus 3 R1. So if you ignore that minus sign in the first, then whatever other multiplier that you are using, in this case minus 3, the second case it was minus 1, and the last case it was just 5. those enter into your lower triangular part of the matrix. And you can verify this, that A is indeed equal to L into U, where A is an lower triangular matrix and U is an upper triangular matrix. So what we were really doing in Gauss elimination without realizing it was, in Gauss elimination we were doing linear operations, linear row operations, and trying to convert it into a series, into a upper triangular matrix. What happened at the same time? My right hand side also changed. Right? My right hand side was -2, -5, -3. At the end of all the operations, I got -2, -11 and 50. Right? Now what that means is, I was really solving the system of equations ux equal to y or y. Okay. What that really means is, if I want to solve a system of linear equations, and the reason why we do this factorization is like this. So I might change, it happens very often in computations, is that the right hand side changes. So in this case my right hand side was given to be -2, -11 and 50. Now suppose I give you a different right hand side. I give you a right hand side 1, 0, 0. What will change? The row operations that you did, they will not change. Only thing what happens is right hand side changes, but the row operations that you did not change, and the upper triangular matrix that you get, that also does not change. So this is again, because it happens very frequently in linear scientific computation, is that I'm just giving a rough intuition of why this so-called factorization is useful. The right hand side will not change. You may have the same matrix and you may have to do several calculations with different values of the right hand side. But each time you don't have to go back and find out which row substitutions you have to do. The row substitutions are going to be the same. And that is why, and the upper triangular matrix that you get at the end, that is also going to be the same. And what are the row substitutions that you did? They were entirely coded in these entries. These entries are basically telling you what those row substitutions were. Row operations that were you doing. What this means is you are doing R2 minus of -3 R1. This means you are doing R2 minus of -3 R1. Here you are doing R3 minus of -R1. Here you are doing R3 minus 5 R2. This is what you are doing. And all of these row operations are basically coded in this matrix L. And the U matrix is what you need anyway to do the so-called backward substitution. So when I do this factorization A equal to LU, I am basically giving you at the same time the upper triangular matrix, and I am also giving you what are the row operations that were carried out. And how is this useful? If I give me any right hand side, so I give you any right hand side now, say I gave you in the previous case there was a specific form of the right hand side. Suppose I give you a different value of the right hand side, B is equal to say 1, 1, 1. How will I use this to solve? I can use this factorization that I have got to solve for the new right hand side. And how do I do that? A equal to LU. So I have LUX equal to B. My B is 1, 1, 1. B is 1, 1, 1. I want to find out X. I know L and U, because that's what I told you. From the previous operations I have done this. I have given you L and U, and I have given you a new right hand side 1, 1, 1. And I am asking you how will you use this information to quickly, without doing too much effort. If you are doing it in a naive manner, I would have to do the row operations all over again. But my claim is I don't have to do any of the row operations all over again. I can just use these two factors to solve for the right hand side. And how is that? You see this. Ux is equal to L inverse 1, 1, 1. And this is my B, right? So let me call L inverse B equal to Y. So let me call Y equal to L inverse B. Do I need to know the inverse of L? I don't need to know I have written it as L inverse B, but I don't need to know the inverse of L. I will just pre-multiply this over here and I'll say Ly equal to B. Can I solve this system of equations? Yes, because it's a lower triangular matrix. So Ly equal to B I can solve. I just start from the top. So I can solve this easily and I can get Y. And once I get Y, I can solve Ux equal to Y, because that is my right hand side now. So by using the same L and U, I don't have to worry about what row operations to do. I don't have to go back and think about what new row operations to do. The row operations are the same. The upper triangular matrix that I get is going to be the same. That is U. The lower row operations are coded in the matrix L. So I just need to solve for any matrix, any right hand side. I just have to solve. I first do the LU decomposition. I factorize A equal to LU by using Gauss elimination. I just code all the row operations are coded in L. The upper triangular matrix that I get is coded in U. I just solve Ly equal to B. It is easy because L is an upper triangular matrix. And if you recall 3 or 4 slides back, we all agreed that solving a system of equations with upper triangular matrices or lower triangular matrices is easy. This I can solve. I just start from the top and I can get Y. Then I solve Ux equal to Y. That is also easy. So you may give me 3 or you may give me a matrix of size million cross million, and you may give me maybe 5 different right hand sides. As long as I can factorize the A equal to LU once, I can reuse this. I can keep reusing this again and again. And it is not very different from factorizing numbers. If I give you a very large number, what do? We mentally try to, when you want to do computations involving them, mentally what we do? We factorize them into prime factors. This is somewhat similar. I am just trying to factorize them into a lower triangular matrix times an upper triangular matrix. Or unlike numbers, these kinds of factorizations are not unique. There are various factorizations which are possible. In your prime numbers, if you give me a number, factorization into the so-called prime, multiple in so-called prime factorization is unique up to an ordering. However, in the case of matrices, this factorization is not unique. It is unique if I agree to store ones along the lower diagonal. So Ax equal to B, I can also write as x is equal to A inverse B. This does not mean I can calculate x without explicitly calculating the inverse of A. So whenever you see a formula, you will see this maybe in several times when you do matrix algebra and so on, you may see expressions involving A inverse B. That does not mean you need to explicitly calculate A inverse. What all you need to do is you need to solve Ax equal to B. Because if you can solve Ax equal to B, the solution of x is the same thing that you can get by doing A inverse B. And of course, all of this makes sense only when the inverse of A exists. When I write Ax is equal to A inverse B, it only makes sense when the inverse of A exists. But the point I am trying to make is, whenever you see a formula like A inverse B, don't rush into calculating the inverse of A. All you need to do is just solve Ax equal to B, which does not require as much effort as calculating the inverse of A, which only requires you to do the so-called LU decomposition over here. And then when you do that, you can get Ax equal to B. And of course, for large systems, there are various efficient methods. For large matrices, there are, depending on certain structures of these matrices, there are specialized algorithms for getting you the LU, for solving these large systems of equations. But LU may not be the standard way in which most numerical solvers they have implemented, but it at least gives you the rough intuition of how things are done. When you use linear equations, you don't really invert the matrix to find the solution. You only have to do certain matrix factorization or decomposition techniques to get the solution of your matrix. So all along, just to recap what are all the things we have done, we have seen vectors, vector spaces. We understood that vector space is really, vectors come from ordered pairs of real numbers as one example. However, it can also be represented as points in space. We know how to add vectors, we know how to multiply vectors and scalars. Then we saw what matrices were doing to vectors. It was doing linear transformations on the vectors. Then we saw what determinants do. Then we saw what happened to linear systems of equations. So now we can also do something else. We could measure angles between vectors. And the way to do that is, if you have vectors, if you have a vector as x1, x2 all the way up till xn, and y as another vector, y1, y2 all the way up till yn. Now I will define the so-called dot product or the scalar product as x transpose y is a real number. It is not a vector. It is a real number. It is equal to x1, y1 plus x2, y2 all the way up till xn, yn. The dot product is this. Now I say that two vectors are orthogonal or perpendicular if x transpose y equal to 0. If the dot product of vectors is 0, then I say that the two vectors are orthogonal or perpendicular. Perpendicular is the term that we normally use in high school geometry. In general, we use the word orthogonal for vectors in arbitrary dimensions or arbitrary vectors. Now this definition helps me to do several things. First, it helps me to measure angles between vectors. First, it helps me to measure lengths of vectors. So length of a vector, we know what it is defined as. It is defined as, there are several ways in which you can define vectors. lengths of vectors, but this is the so-called Euclidean distance of the vector. This is nothing but just the square root of x transpose x. Right? And this is always well defined because this whatever is under the square under the radical sign is a non-negative number. So you can always take square roots because it is going to be these are obviously going to be non-negative numbers. You can always take square roots of this. So you can define lengths of the vector this way. Now what about angles between vectors? How do we define angles between vectors? In 2 dimensions, of course, you know how to do that. In 3 dimensions, you can do that. There are standard rules in geometry and so on. You can do these. In higher dimensions, if you want to so-called visualize angles between vectors, what do I do? And the vectors have to be non-zero, right? There's no point in trying to say what is the vector angle between this and this zero vector. That does not make sense. If you want to talk about angles between vectors, both the vectors have to be non-zero. Now, again, let's go back to the length of the vector. If the length of the vector is non-zero, then clearly the vector is a non-zero vector. Because length of the vector is non-zero, which means this number is non-zero. Therefore, at least one of these entries x has to be non-zero, so it cannot be the zero vector. So any non-zero vector has a non-zero length. Likewise, non-zero, if the vector has non-zero length, then it is not a zero vector. So if you want to find angles between 2 vectors, say x and y, and I know that they are non-zero vectors, which means length of the vector x is not equal to 0, length of the vector y is not equal to 0. The angle between 2 vectors can be defined as, the cos of the angle between this can be defined as x transpose y by the length of x times the length of y. And that's what we can also prove there's a famous inequality called the Cauchy-Schwarz inequality, which says that this is less than 1 and greater than minus 1. Which again makes sense, right? We have always defined cos of an angle as something between minus 1 and 1. If the angle is 90 degrees, the cosine is 0. If the angle is 0, then the cosine is 1. If the angle is 180 degrees, the cosine is minus 1. So again, this is a rough this definition over here is basically generalization of whatever geometry, 2-dimensional, 3-dimensional geometry that we have seen. If 2 vectors are perpendicular, if the angle between 2 lines or 2 rays or 2 vectors are perpendicular 0, then the cosine is 1. If it is 180, the cosine is minus 1 and so on, and that again comes down from over here. If the 2 vectors x and y are perpendicular, if the dot product in the higher dimensions, these are just a cartoon representation. In higher dimensions, obviously, I can't visualize them, I just cartoon figure. I draw this to have the same intuition that in higher dimensions also, 2 vectors are perpendicular if the dot product x transpose y is 0. If the 2 vectors are collinear, that is, they are pointing in the same direction, what does it mean? It means one vector can be written as a positive multiple of the other. You substitute it over here, you will get the number 1. If one vector is pointing in the other direction, you will find the cos theta is equal to minus 1. Because one vector will be a negative multiple of the other, you will get the minus 1 over here. So at least this definition of the cosine of an angle between vectors in arbitrary dimensions serves as a useful generalization of our concept of how to measure angles between vectors. And more importantly, if 2 vectors are perpendicular to each other, then the cosine of the angle is 0, or equivalently dot product is 0. Okay, so we saw one factorization of a matrix, which was the LU decomposition, which was useful for solving linear equations. Now there is another factorization of a matrix, which is now what we will see that. Suppose I give you 2 vectors a1 and a2, right? And they could be pointing like this. This is a1 and this is a2, right? And my matrix A is a1, a2, right? Now I'm going to factorize this in a certain specific manner. From these 2 vectors, I'm going to get a set of perpendicular vectors, right? Now how do I get the first perpendicular vector is, I'm going to take it as I'm going to get another vector which is q1, and I'm not just going to make it perpendicular, I'm also going to make it of unit length, because I like to have things of standard unit length. So I'm going to keep the length of the vector 1, and I'm going to start from the vector a1 itself. So how do I get q1? q1 is just a1 by the length of the vector a1, I get a unit vector. Now, so I have got A1 over here. In this case, Q1 is a unit vector of length 1. Now, I want to get another vector Q2 which is perpendicular to Q1 from these two vectors only, from these two vectors A1 and A2. So, how do I do that? I take the component of A2 along A1. What is the component of A2 along A1? What is this? This length of this vector is mod A2. From high school geometry, we know that this is A2 cos theta, right? This cartoon picture is, I mean, we know we have done this in 2 dimensions, but this cartoon picture is basically also what is going on in higher dimensions. That's why the definition of the cosine of the angle was important. This could be representing vectors in n dimensions, in 3, 5 dimensions, 6 dimensions. I don't care. So this is the project. The component of A2 along A1 is A2 cos theta times Q1, because Q1 is a unit vector now. The component of A2 along A1 is A2 cos theta times Q1. Q1 is a unit vector. So what is cos theta? So this is again cos theta is angle between the vectors A1 and A2. Or yeah. So now what I will do is, from A2 I will subtract the component, this component over here. Or another way to do that is, I would have just from A2 I am going to subtract the component along A1. So this component. So A2 I am going to write as this vector times some other vector. Now what will happen to this vector over here? So A2 minus from A2 I subtracted the component along A1. So in some sense, whatever I can explain along A1, I can explain along A1 of A2. Whatever A2 I can explain along A1, I have done that. So what will be the residual thing? This will be perpendicular to A1. So the component of, if you after subtracting the component of A2 along A1, the residual thing is going to be perpendicular to A1. And this again, I can get this component, and then subtract from A2 I can subtract this, and I can get the component, I know that it is perpendicular to A1. So this I can just, I will just, if I have a third vector, I do this, I get the first 2 independent perpendicular vectors, then I will find the component of Q3 along, try to get it along Q1 and Q2 and subtract it, and then whatever is balanced, that will be the balance vector. So let me just try and explain this properly in general terms. So I have A1, A2. I am going to get 2 vectors. I am going to get 2 vectors perpendicular to each other, each of them has unit length, and the first vector I got by just A1. So what can I say about A1 is equal to, suppose it is some alpha times Q1. What is Q1? Q1 I know is equal to A1 by mod A1. So alpha is just equal to the length of this. Another way to get that is, say this alpha 1. Another way to get that is just, I know what is alpha 1 is equal to mod A1. So let me define Q2 prime as just equal to A1 minus the component of A1 along Q1. And what is the component of A1 along Q1? Sorry, A2 along Q1. This is A2 and this is Q1. Q1 is a unit vector. So what is the component of A2 along Q1? A2 transpose Q1 times Q1. So the component of A2 along Q1 is A2 transpose Q1. This is the cos of the angle between A2 and Q1. I know Q1, and this is this component of, this is Q2 prime. This is the component A2 Q transpose Q1 times Q1 is the component along Q1. Subtract that from A2, this is I get Q2 prime. Now I want to get a vector of length 1 along Q2, so I just take Q2 prime divided by length Q2. So this makes the length of the vector Q1 also 1 and the length of the vector Q2 also 1. So from the two vectors a1 and a2, I have given you two perpendicular vectors, each of which are representing of having unit length. Now the question is, how do I represent these two vectors or matrix? Now I am going to call this matrix Q is equal to Q1, Q2. The original matrix was A, which was A1, A2. If I have a third vector A3, which was also, if I have a third vector A3, how do I get the third vector Q3? I take Q3 prime, I take A3, subtract the component of A3 along Q1, which is A3 transpose Q1 times Q1, subtract the component of A3 along Q2, which is A3 transpose Q2 along Q1. So A3, I have taken A3, whatever I can explain along Q1, I take that, whatever I can explain along Q2, I take that, I subtract these two. This has to be perpendicular to both Q1 and Q2. If there were three vectors Q1, A1, A2, A3, they are independent. So I first take A1 as the first vector Q1, then I take the component of A2 along Q1, subtract that from A2, I get, and then normalize it, I get my second vector Q2. Then I get the third vector, I take the component of A3 along Q1, the component of A3 along Q2, subtract those from A3. This has to be perpendicular to Q1 and Q2. And then Q3, my third vector Q3, if I want to get a vector of unit length, I just divide it by the length of the vector Q3. So how are these matrices this is called the Gram-Schmidt orthogonalization process. So how are these vector, how is the vector A and Q, how are the matrices A and Q related? So that we will see over here. And then with that we will think that will be a good place to stop. So A is of size n cross n, and Q has columns Q1, Q2, Qn, and this is of size n cross n. I know that Q2 is perpendicular to Q1, Q2 transpose Q1 equal to 0. I know that Q3 is perpendicular to both Q2 and Q1, and so on. So I know that all the columns are perpendicular to each other. So this is called an orthogonal matrix. Q, such a matrix Q is called an orthogonal matrix if any two columns are perpendicular to each other, and because all the lengths of Qi are equal to 1, Q is called an orthonormal matrix. Normal because all the lengths have been normalized to be equal to 1. So all the Qi equal to 1. So Q is an orthonormal matrix. So if I want to write A equal to Q times R, that is the so-called QR factorization, and that will be, how will I get that? R, what kind of a matrix will R be? We will see that. Right? So A1, A2, all the way till An. It won't be a diagonal matrix. Q1, Q2, Qn. So we know what is this, right? A1, if you expand this out, you know, A1 is equal to it's only a function of Q1. It does not depend on any of the others. So A1 is, if you want to write it as alpha 1 Q1, it has only alpha 1. If I want to write A2 as alpha 1 Q1 plus alpha 2 Q2, that will not have any component, it will not be a function of, it will be plus 0 Q3, right? Because Q3 was not used, Q3 did not, we did not define Q3 from A2. A2 was just, Q2 was got only from A1 and A2. So likewise, I can write A2 as Q1 plus Q2, some combination of Q1 and Q2. Likewise, I can write A3 as some, alpha 1 prime Q1 plus alpha 2 prime Q2 plus alpha 3 prime Q3 and so on. Right? So now, if I want to ask this question, what is this? This will be an upper triangular matrix, because I can think these all will be zeros, and what will go in my R matrix will just be, in this case it will be A1 transpose Q1, and this will be 0, and in the second case it is going to be A2 transpose Q1, A2 transpose Q2, and this will be 0. So this will be an upper triangular matrix, R will be an upper triangular matrix. So let me maybe clear this up and then it will be. So this is an, so A can be factorized as Q times R, where the columns of Q are orthonormal. Each column is perpendicular to each other, and the lengths of the vectors the lengths of each of these vectors is 1, and R is an upper triangular matrix. Now this factorization will also be involved later on when we do least squares. Why this factorization is important, we will see that. So the LU decomposition was important for you to be able to solve linear equations. The QR factorization will be important to solve certain other kinds of equations called the normal equations, which we will see in the second half of this class.